Objective 8.1, Graphing Exponential Growth Functions. In Objective 8.1, we want to be able to do two things. We want to be able to sketch a graph of an exponential growth function, and then we want to be able to state the domain and range of that function. So let's take a look first at what an exponential function looks like algebraically. I have four choices for you here, and I'm asking you which of the following is an exponential function. Well, I think it's safe to cross out number 4 because there's no exponent in number 4. We just have y equals 3x minus 12, no exponent, so I doubt that that's an exponential function. Okay, but what about the other three? Which of these three seem to you to fit an exponential function? Well, they all three have exponents in it, but the key to an exponential function is that the variable is in the exponent spot. So even though these two have exponents, the exponents themselves are numerical, and so that actually puts them into a different category like quadratic or fifth power types of functions. Here we have the exponential function because the x is in the exponent spot. So if we take a look at the general form of an exponential function, it's going to look like this. Y equals a times b to the x. We'll have x in the exponent, so whatever our independent variable is going to be will be somewhere in the exponent. We have this variable a. That a is called the initial value, and it cannot be equal to 0. So you have to start with something, and that's exactly what this means. This initial value means that it's the starting amount before the growth starts to take place or the decay starts to take place. Okay, so you have to start with something. You cannot have an a equal to 0. Okay, and then your b is called your growth or decay factor. Depending on which type of exponential function you have, growth or decay, this b is the factor at which things will grow or things will decay. And here we have to make sure that we have a b value that is positive, so b must be greater than 0, and b cannot equal 1. Because if you have a growth or decay rate that is a factor of 1, you're just multiplying by 1 over and over again, and it doesn't actually change. Okay, now graphically, we can take that general form of the exponential function and we can adapt it a bit to show what happens with our graphs. So if you remember from previous functions in 2a, we can do things like subtracting h with the x. Well, that now happens here in the exponent spot. So that minus h is up here with the x in the exponent spot. We can also add k on to the end of a function, so that's what this is. And then we've still got our multiplying by a here out in front. A, h, and k will have the same effects on our graphs as it has had in the past. So let's review that real quick. For our a value, remember a actually will have two different effects depending on what the number is. If the a is negative, then that means that our graph is going to reflect through the x-axis. Okay, so whatever the normal a b to the x would have been, if my a is negative, then that's going to be flipped around through the x-axis or reflected. Also, The A is going to give us some idea as to how steep or how gradual the curve is going to change. So the bigger the absolute value of A gets, the steeper the curve. The smaller the absolute value of A is, then the more gradual the curve. H, again, is going to move our graph to the left or the right. And remember that the minus is part of what the general form is. So the H is always opposite of what it looks like in the general function. And then the K is going to move our graph up and down. And because that's a plus K, that's exactly what it looks like. Okay, so let's start with a basic exponential graph. And then we'll use that to come up with other graphs based on transformations. Okay, so we're going to graph y equals 2 to the x power, and then we're going to state the domain and the range. So let's just start the old-fashioned way. Let's just come up with a table of values, and I've given you half of the values already. I've chosen some x values for you to try. Go ahead and take a minute and pause your video and fill in the y values that correspond with these x values on your guided note sheet. When you have them filled out, go ahead and come back and we'll check to see that you have the right answers. All right. So when you put in -2 for x, 2 to the -2 power, remember means we're going to end up with, means we're going to end up with a fraction. And so 1 over 2 to the +2 power is going to give you 1/4. And then similarly, the -1 means 2 to the -1, or 1 over 2 to the first, so that's 1/2. And then a 0 exponent always gives you 1. 1 will give you 2, and 2 will give you 4, 3 will give you 8. So these are our ordered pairs right here in the table. So now on your graph, take a minute and plot those points. Okay, so your points should end up looking a little bit like this. Okay, and so once you have those points in place, then you can draw a smooth curve through them, which is going to look something like this. Now, do you think that this curve is ever going to touch the x-axis? We can see that it's kind of curving in here, and it seems like we're getting closer and closer to the x-axis here, and if we were to put in more x values, we could see what the actual y's are. But do you think we'll ever get to a point somewhere out here where this blue graph will actually touch that x-axis? Well, the answer is no. And the reason for that is because when I have a point that's on the x-axis, it means that that y value is a 0. But yet in the equation, y equals 2 to the x, is it possible to put in any value of x that will end up making 2 to the x equal a 0? And the answer is no. You cannot come up with any number for x that will make 2 to the x power give you a 0 answer. So that makes our x-axis an asymptote, meaning it's a barrier, it's a line, an imaginary line, that the graph is going to get closer and closer and closer to as it comes down here, but it's never actually going to touch it, it's never actually going to cross through it. So that gives us an idea then of what our domain and range are going to be. For domain, we're looking at x values. Well, does there appear to be any limit as to what x values we could possibly use if we could expand this coordinate forever and ever and ever? No, there's no limit. So our domain for exponential functions is going to be all real numbers. Okay, but what about our range? What happens with the y values? Well, that's where we have some limitation because we now have this x-axis that is a limit to how far the y's can go. So our graph stays entirely above the x-axis. And in terms of y values, that means that y is bigger than 0. We never actually touch the axis to make y equal 0. And if we can't touch it, then that means we can't cross through it. So our graph will never get down here below where the y's would be less than 0. So the range of our exponential function is that y is greater than 0. And this is pretty much always the case with a basic exponential function, regardless of what number you have in for the base, for the b. Your domain is always going to be all real numbers, and your range is always going to be y is greater than 0. Okay, but now if we take that and we specifically talk about exponential growth, you can see here that what we just graphed is an example of exponential growth, because as my x's are getting bigger, my y values of my points are getting bigger. So we have things that are growing here because as time passes, we're getting more and more of whatever this y value represents. So this is an exponential growth situation. And we can always tell that that's what we're going to be dealing with in the equation if the b value that we're using is bigger than 1. So in this case, what we just graphed, our b value is 2, and 2 is bigger than 1. So we know this is an exponential growth function. Okay, so now let's use our y equals 2x and do a few transformations and see how this affects the graph. So in this case, we have the equation y equals 2 to the x plus 2. Well, we already know what the basic 2 to the x graph looks like. That's what we just graphed. But what effect will plus 2 have on the graph? Well, hopefully you realize that that's a k value. That k value is 2. And the effect of k is to move the graph up and down. So since k is a positive 2, it's going to take the basic 2 to the x graph and move it up 2 units. So here's the basic graph that we just graphed a minute ago. And now if I take every one of these points and move them all up 2 units, then I get my new graph, which is the one here in orange. And this is the graph of 2 to the x plus 2. Okay, now how does that affect the domain and range? Okay, well, have I done anything that's going to limit my x values? No, moving the graph around does not change the fact that I can use any x values. So the domain is still going to be all real numbers. Okay, but what about the range? Normally, our range is that y is greater than 0. Have I moved my original graph in a way that would also move this asymptote line? And the answer is yes. If I use a k value to move my graph up and down, then that means this asymptote also is going to move up or down. So if my entire graph has just been moved up 2 units, then my asymptote has also been moved up 2 units, and it's now going to be at 2. So my graph now has to stay above the y of 2 rather than the y of 0. So anytime you have a k value, your range is going to be affected. H values, which affect x, left, right, and left movement, that's not going to change anything because our domain is already all real numbers. But that k value is going to affect what your range is depending on how far you move up or down. So for domain and range, domain is going to be all real numbers, range is going to be y is greater than 2. Okay, let's try another one. This time we have the equation y equals 2 to the x plus 4 power. So now which number have I been given this time? Hopefully you recognize that since that is up in the exponent spot with the x, that makes it an h. And because it's plus 4, that means the h must have actually been negative 4. So what effect will an h of negative 4 have on my 2 to the x graph? Well, again, here's my 2 to the x graph. An h of negative 4 means that everything is going to move to the left by 4 units. So I take each of my points, I move them all 4 units to the left, and my orange graph represents my new graph. Now, what is the domain in this case? Well, again, nothing has affected what I can use for x, so this is still going to be all real numbers. Okay, and what about my range? Well, since I didn't have a k value this time, my range is not going to change. So my range is still going to be that y is greater than 0. So domain is all real numbers, range is y greater than 0. Okay, let's try one more. Let's throw a bunch of stuff into this one, see if we can figure it out. So I've got y equals negative 1 times 2 to the x minus 1 plus 5. Okay, so what are all of the extra numbers that I have here? Do I have an a? Yes, that a is a negative 1. Do I have an h? Yes, in this case the h is a positive 1. How about a k? Do I have a k this time? Yes, my k is going to be 5. So if I have negative 1 for a, what does that do to the 2 to the x graph? Well, this is going to reflect it. Flip it through the x-axis. Okay, my h of 1 means I'm going to move to the right 1 unit, and my k of 5 means I'm going to move up 5 units. So once again, let's start with the 2 to the x graph that we know. Usually we want to start with a because if there's a reflection, it's easiest to do that first. So let's reflect our graph through the x-axis first. That's the effect of having a equal to negative 1. Okay, and then we'll take this new orange graph and we'll move it 1 unit to the right and 5 units up. And so our graph is going to end up there. Oops, sorry. Take another minute to look at that. So we've reflected our blue through the x-axis to get it to curve the other way. And then we moved everything 1 unit to the right and 5 units up to end up with this orange graph. Okay, now what about domain and range? Well, again, domain, nothing has changed. There's no more restriction on x, so we still have all real numbers. There's very few situations I can think of where your domain for an exponential function is not going to be all real numbers. Okay, but what about the range? Okay, well, 2 things affect the range this time. One, what we talked about a minute ago, is the fact that we had a y. We had a k, which affects the y. That k was 5, So the asymptote that was normally at 0 also got moved up 5, just like all these points did. So the line here at 5 is now a new asymptote. Okay, that's the boundary line now instead of the x-axis. But on which side of that line are we this time? Well, this time we're below that line because of the a value of -1. When we reflected our graph, then that means we end up below the asymptote line rather than above it. So instead of y being greater than the k value, we end up with y being less than the k value. Sorry, I don't know what happened on that. Okay, so our domain is going to be all real numbers still, but our range now is going to be that y has to be less than 5. All right, well, I hope that gives you enough information to be able to move on to the practice. If you have any questions over some of the concepts in this video, make sure you ask questions during class. And then during next class, you should be able to work through the 8.1 practice in your booklet and make sure that you show Mrs. Gordon your 8.1 work when it's completed so you can get it checked off the list. We'll see you next class.